Perfect. Yeah, I think we can get started.
Let me share my screen. Can you see my screen?
Yeah.
Yep.
Perfect. Yeah. So just to repeat what we talked about before the break. So we're talking about eligibility traces. Eligibility traces is a way to get higher sample efficiency, and it's especially popular. It works well for tabular and for linear methods, and it's there is it's strongly related to multi-step updates, which have been covered before. In fact, it implements a particular like the values it computes are very similar to the Lambda return algorithm, which performs updates with the Lambda return, which is a particular form of compound multi-step update target that uses a summation, a weighted sum over all possible update targets. Before I sort of go on into sort of the second half, which I'm going to talk more about the relation between eligibility traces and multi-step updates. Are there any questions on what I talked about before the break? Like high level, is it clear? Okay, if there's no questions.
Okay, so there's a question from the class. Yeah.
I didn't quite understand where the difference between this return that we saw and the Monte Carlo return equation.
Okay, so the question is like what's the difference between the Lambda return and the Monte Carlo return?
So the Lambda return is a parameterized update target. So depending on the value of Lambda, like for each value of Lambda, it's a different update target. So Lambda takes on values between 0 and 1. And in fact, if you set it equal to 1, it's equal to the Monte Carlo update target. If you set it to 0, it's equal to a one-step update target. And if you set it something in between, then the update target is something in between as well. So, think about it as an n-step update target. If you just take the general formula for an n-step update target, then you have the parameter n. And if you set n to infinity, it becomes the Monte Carlo update target. If you set n to 1, it becomes a one-step update target. And you can also set it something in between. So the same is true for the Lambda return. It's a parameterized update target where the particular shape depends on the value of Lambda. So good question. We'll talk about that a little bit further down in these slides as well, I believe. So this is something I worked on during my postdoc. I worked on this together with these four guys over here, Rupam, Patrick, Marlas, and Rich. And they're all, they're all working again in Edmonton, actually. They're all moved out in different ways, and now they're all back in Edmonton. So the outline is going to be, I'm first going to talk about True Online Temporal-Difference Learning, which is sort of this variation of eligibility traces that is like a better version. And in the second part, I'm going to talk about doing multi-step learning for nonlinear function approximation, because as I said before, you know, it's not so common in DeepRL to see multi-step updates or eligibility traces. And I'm going to talk a little bit about that, why that is, but also what you could potentially do, you know, what you could do to still get some multi-step updates. Okay, so this is a presentation I gave before sometime at this topic. So it starts very general with sort of what is a Markov decision process. Now, this is all basics that you're already familiar with. So I'm going to go rather quickly to these first slides here. So policy and mapping from state action to a probability distribution, the return. This is the definition of a state value function and an action value function, which is just the expected return conditioned on the state versus conditioned on a state action pair. Now, how do we estimate a value function when we do function approximation? So it's the typical approach. You have an error function, and in the case of RL, it's the difference between the true value of a state minus your estimated value of the state, where the states are weighted according to the stationary distribution induced by your policy. So this just talks about the prediction problem. And the control problem follows very straightforwardly from that. But yeah, we're just talking about the prediction problem for now in this slide. So using this error function, you can then use stochastic gradient descent. And if you sample from a stationary distribution, you get the following following update equations, which you sort of may recognize as being, yeah, this is sort of the form that you probably recognize. Yeah, because this one is unknown, so if you want to do a true gradient descent, you would use the true value of the current state. But because you don't know this, you want to estimate this, you use an update target. So that's why in the new book, like the new version of Rich's book, it calls this semi-gradient descent rather than full gradient descent, because you're using this estimate over here. And with linear function approximation, this gradient over here just becomes your feature factor, and this value estimate you can just write as this, so it slightly becomes takes a more simpler form. And yeah, if you want to take if you take the full return as your update target, you get an unbiased estimate. But with temporal difference learning, we sort of exploit the structure, and we get sort of this form that you're familiar with. The one-step update target are sort of a three-step update target, which you can see over here. Now, moving on to TD Lambda. So these are the update equations for TD Lambda. So this uses eligibility traces. As I told you before, like previously, like in the previous edition of the book, eligibility traces, the letter E was used. In the new edition, the letter Z is used. But in these slides, I still use the old notation. So it's just the letter E. And so, yeah, this is the TD Lambda for linear function approximation. So I before the break, I showed you for the tabular one. This is a slightly more clean equation. And so, yeah, you have the update. So your delta here is your TD error. the eligibility traces is discounted, but the current feature factor is added as well. So, you know, features that are recently visited have a high value, features that are not recently visited have a low value. And in the tabular case, your feature vector is just a one hot factor where each feature corresponds to a particular state. And then your update equation is proportional to the value of your eligibility trace. So this is the formula for TD lambda. And yeah, like I said before, this is it's a very strange update equation in a sense. It doesn't look like the one that was derived in the previous slide for the one-step update target. So what's going on here? Is this even a valid method? Well, yeah, it's different than the general update rule. I mean, it is a valid method because it sort of the values it computes are very closely related to the lambda return algorithm. So this one is, I showed you this before the break as well, but now we have the same update, but now for linear function approximation. So, but this is the lambda return that I talked about before, but now rather than just the value of a state, we have the inner product between a weight factor and a feature factor. So that's the lambda return algorithm. And yeah, so as I said, for the lambda return, if lambda equals to 0, this is equal to the one-step update target, the one-step return. And if lambda equals to 1, it's equal to the full return, or the Monte Carlo update target. And the theorem says that for small step sizes, theta t, so the value you compute at the end of an episode computed by TD lambda, is approximately the same as the value you compute by the lambda return algorithm. And sort of this approximately the same, that is also where sort of the limitation of this theorem lies. Because for small step sizes, that's not generally the region where you want to be, because if you want, the whole reason we want to do multi-step updates and eligibility traces is that we want to get high sample efficiency. And if you want to get high sample efficiency, you typically want to use larger step sizes as well. And so the theorem is only true for a region where actually that's the less interesting region. So that's one limitation, and that's something that that we're gonna sort of try and correct in the rest of the slides, and that's what's sort of the true online temporal-difference learning is about. The other limitation is that the equivalence only holds sort of at the end of an episode for sort of the final value. But you ideally want something like TD lambda performs update. It's an online algorithm. It performs update at every time steps. And ideally, you want a guarantee. You want to make sure that those in-between values, those online values, they make sense as well, and they're grounded theoretically as well. So you know those are good estimates as well. So, and that's currently missing from this theorem as well. So these two disadvantages are going to be addressed in True Online Temporal-Difference Learning. And so how to set lambda? This is something we addressed before the break as well. Lambda, just like the value of n, it's a trade-off. It balances a trade-off between bias and variance, and it will be different from domain to domain. So you have to tune it per domain. And yeah, lambda, it only influences the speed of convergence. But in the tabular case, well, if you're doing function approximation, it can affect the asymptotic performance as well. In the linear case, that's not typically what you see, because mostly things are well behaved. But it's, if you're gonna use it for nonlinear function approximation, it could affect the asymptotic performance as well. But yeah, in the tabular case, it only affects the speed of convergence. Yeah, that's some theoretical results for the linear case. So for lambda equals to 1, it converges to the least mean squared solution. For lambda smaller than 1, it converges to a fixed point. So in the linear case, you still have convergence guarantees, although that fixed point can be a little bit removed from your optimal fixed point, like the least mean square solution. Yeah, so online versus offline methods. We used this term before. Here I define it. The online method is that the value of each visited state is updated at the time step immediately after the visit. And then for an offline method, you only update it at the end of an episode. And it's actually like, if you do prediction, it doesn't matter that much. But if you do control, and if you have very long episodes, you really want to have an online method, because you get all kinds of data during your episode, and you want to be able to update your value already during the episode and exploit the data, because else convergence can be very slow, because your policy generates the data. So if you have a poor policy, you're generating data in sort of a poor region, and that can contribute to further slowing things down. So doing online updates is really important, and yeah, so getting a good online method is very important. Now, TD Lambda is an online method, but the Lambda return algorithm is an offline method, and it has to do that the Lambda return, you can only compute it, it's an infinite sum, and you can only compute it at the end of an episode. So there is some disconnect here, and we're gonna look into that. So the first question that I asked myself in this research, is it possible to construct an online version of the Lambda return algorithm that approximates TD Lambda at all time steps? So not just at the final time step, but at all time steps. And well, the answer is actually yes, you can, but it is pretty challenging, because to compute the theta t, you can't use data beyond time t, because it's not observed yet. At the same time, we want to have a multi-step update target that looks many time steps ahead, maybe till the end of an episode. So these two things appear to be in contradiction with each other. However, there is a trick you can use to combine these two, which is that you use update targets that grow with data horizon. So normally you have a particular feature factor, and you have a single update target for that. But we now switch to a different view, where we use multiple update targets for a single feature factor, and I'm going to call these interim update targets. And the horizon of an update target grows like the further you go into an episode, like the more data you observe. So the superscript here refers to the data horizon, which is the time step up to which data is observed, and it can make a interim lambda return as well. So the interim lambda return with a certain horizon h. So it doesn't use. So I've rewritten my lambda return such that it doesn't use data beyond time step h. And so this is sort of rewriting of that. And I can now do update sequences as follows. So this is the idea of redoing update targets. So I have at time step 1, I only use data up to time 1. So I have a lambda return with a data horizon of 1. So it's a simplified version. And then at time 2, I basically start from scratch again, because my initial theta, so if there is a 0 at the bottom, these all take the same value. I'm just redoing my update targets. So at every time steps, I'm recomputing what my update targets are, given the new data horizon, and then I start from scratch. I start from my initial value, and then I do these update targets. So this is a way where you combine having an online method, so doing updates at every time step, but still doing multi-step update targets, so they grow over time, like the data horizon grows over time. Now, the only disadvantage of these methods is that it's super inefficient, because I'm redoing update targets. I have to recompute these lambda return, these interim lambda return update targets, and sort of the computation grows with per time step grows with how far I am into the episode, because I the number of updates I perform is equal to the time step. So this gets very, very expensive very quickly. The good news is that you can actually, there is a way, an efficient way. Sorry about that. Let me just move back. There is an efficient way to jump. Let's go here. So there is a efficient way to go from this one to directly compute this one from this one and this one from this one. So you don't actually have to do all these in-between steps. And that is what the True Online TD Lambda does. So, but first, yeah, we have now, let me just figure something out here. Wherever I press, it only goes forward, and it doesn't seem to go backward. Okay. All right. So let's just do it like that. Okay. So we now, with this trick, we have an online version of the lambda return algorithm that uses interim lambda returns, and it performs a number of time steps equal to the, so it performs it redos all the updates. So it redos at every time step, redos all the updates it has done before, but then with interim lambda returns with the current data horizon. So we now have built an online version of the lambda return algorithm, but yeah, like I said, it's very inefficient. Now, if we compare the online algorithm with the offline algorithm, sort of to get a better understanding what these methods do. So this is this plots the error on a 10-state random walk task for the first 3 episodes. And so you see the green one here is the offline algorithm, and it the error, like its values remain the same during an episode. So its error also remains the same. And then it performs all the updates at the end of an episode. So then the error makes a big jump. Then for the second episode, again, no updates during the episode, but then until the end of the episode. And the same here again. So the red one is the interim the online lambda return algorithm. And you can actually see that at the end of an episode, it hits exactly the same points as the offline lambda return algorithm. So there is an exact equivalence between the offline and the online lambda return algorithm at the end of an episode. But now I'm also updating values in between. And yeah, like I said, this is especially important for control methods where you want to, you want to improve during the episodes already, because it affects your data distribution, among others. And it also affects sort of the actual return you observed. So we've shown now that we have this online version of a lambda return algorithm. I've also showed the TD lambda algorithm, and it, it's approximately equivalent to the offline algorithm, and it's at the end of an episode, and it's approximately equivalent to the online algorithm. But what we ideally want is an exact equivalence with the online algorithm, because we know the online lambda return algorithm, it's actually built on a solid theoretical basis of...
Hello? Check.
Yeah.
Hey, there's a question from the class.
Okay.
Can you explain again the intuition behind like the way you made the online lambda return algorithm that matches the TD lambda?
Okay, so
Like what was the intuition behind that? Basically, I completely didn't understand why exactly it is now resembling the TD lambda algorithm.
okay, so the question is like, what is the intuition behind online lambda return algorithm, and why is it resembling TD lambda?
Yeah. Well, so the online lambda return algorithm, like it was really built to be equivalent to the offline algorithm at the end of an episode, and be approximately and sort of make updates during the episode. Like the fact that it turned out to be rather similar to TD lambda, that's actually that wasn't I didn't try to build it like that. It just turns out to be like that. And this sort of shows that. So it was sort of a surprising result. It shows that TD lambda actually does something very similar to the online lambda return algorithm, and that sort of explains as well why it actually works as well as it does, because the online lambda algorithm is it has a solid theoretical foundation. And so it's, I guess from that perspective, it's not surprising, but nobody had really shown it before. And like I said, the online lambda return algorithm, it wasn't really built to sort of approximate TD lambda. It was built to have to be exactly equivalent to the offline lambda return algorithm, and also do updates in between. So it's just when I write algorithms, I write them in a way that makes sense to me, and the online lambda return algorithm makes a lot of sense. And so it was sort of good to see that TD lambda, which takes a completely different approach with eligibility traces, it actually turned out to be very equivalent to sort of this theoretical approach that makes a lot of sense. It's not exactly equivalent, and so this is where I'm gonna introduce a variation to TD lambda, like a different type of traces, Dutch traces, where the equivalence is actually exact, which has all kinds of advantages. But it wasn't really when I first made this graph and I saw that, in fact, TD lambda is almost equivalent to it. I was kind of surprised. I didn't. It was a surprise. I didn't build it with that intention. I build it with the intention. It has to be equal to the offline lambda return algorithm at the end of an episode, and it has to be sort of a theoretically sound method. And then I just try to build something that make most sense to me. And what made most sense to me was sort of using these interim lambda returns and redoing updates, because this is sort of if you think about, if you don't worry about computation time, you just want to build best possible algorithm with the data that you have. This is the thing that I would do. Like you construct a lambda return algorithm that you construct a lambda return algorithm with up to the current horizon, and then you redo from scratch all your updates. Like this is how it was constructed as, you know, this is the most sensible thing to do if you have all this data. Now it's, and if you just ignore computational cost. And this led me to this algorithm, and then sort of as a coincidence, it turned out to be very similar to what TD Lambda does. And actually, if you make your step size really, really small, it becomes exactly similar at every time step. So I don't know to what degree that answers the question, but yeah, it's yeah, the idea of, I mean, so here is one thing to understand, because there is an alternative that you could think of, which is like, what is novel here is the idea of redoing an update. And you could ask yourself, okay, when I get more data, why not just do additional updates? Sorry, go back one more time. So why not just do additional updates, right? So why? Because I start from my initial state and I redo my updates. And that doesn't seem to make, might seem illogical at first. Like, why not just do additional updates? So I still do these updates, but then I just, with my new data, I compute sort of this lambda return algorithm with a new horizon, and then I just do additional updates instead of redoing those updates. Now that actually doesn't work. That doesn't work well, and the reason is that you're sort of like you want to like, this is really a better update target than the one before. So if you're redoing an update, sorry, if you do an extra update, you still have that update with sort of the more poor update target in there as well, which has still its effects in your final theta. So rather than that, you sort of want to forget about the updates that you've done, because these are simply better update targets. They use more data. So you want to forget about the update targets that you've done. So there's no trace of those updates anymore in your theta, and you just redo your updates as if you've never done these previous ones. And you do that by just starting from your very first theta. And that turns out to work very well. So that's why sort of, yeah, the concept of redoing updates, starting from scratch again, that's sort of maybe something strange, something to, you have to stare at for a little bit to wrap your head around. But, you know, it's actually, yeah, this is the only way it works. Like if you just do additional updates, you're never going to get that same performance. And on top of that, like, this is, you know, the fact that with TD Lambda, people never really understand exactly what it did, but as you saw in these results, it actually, the updates that you perform makes it jump from this point to this point to this point. So it is actually an approximation of this process, like an efficient approximation of this process that simply jumps from this point to this point to this point without having to do all the, without actually having to redo updates, but it's equivalent it's equivalent to that process. So, you know, this was some extra insight that we gained from doing this research, is that actually TD Lambda, this is something that it does all along. Yeah, I hope that answers to some degree your questions. Yeah, it is it's a little bit, yeah. If you don't get it right away, you know, that makes a lot of sense. You just have to stare at it at some time, sometimes to wrap your head around it. But yeah, so we have this now, whereas before the theory only said something, the theory of TD Lambda only said something about sort of the terminal state, that there was this approximate equivalence. Now we have an online Lambda return algorithm, and actually it's approximately the same now at every time step. So the next thing is that we want to have exact equivalence. So yeah, so we extended the theorem, and we said that for small step size, the online Lambda return algorithm behaves like TD Lambda at all time steps. So which is great, but now we want to get rid of the dependence of the small step size. We just want the equivalence to hold always. And so the reason that we want this is, so here I show sort of for a very simple task, what happens for larger step size. So this shows the error, so smaller is better. And I plot here for lambda equals to 1. I plot the performance of TD Lambda and of the online Lambda return algorithm. And what you can see here is that with lambda equals to 1, you actually can get a perfect performance for if lambda equals equals 1, like the optimal step size is 1 here, and you see performance goes up with higher step size. However, for TD Lambda, like you can see for small step size, there is an equivalence between TD Lambda and the online Lambda return algorithm, like the theory predicts. But for high lambda, the performance of TD Lambda becomes very bad, and the error sort of can blow up and go to infinity. So this shows that, yeah, the online Lambda return algorithm, that is actually, it's the better algorithm, and we really want like we want to get exact equivalence to the online Lambda return algorithm, because then we sort of unlock these high values of your step size, which gives really, really great performance. Because if you would have TD Lambda, you would sort of tune your step size, and you would get stuck at a value of around 0.1 here. With the online Lambda return algorithm, you can almost make it completely go to 0 if you use a very high value of alpha. So this is this region really wants. So we want to build a better version of TD Lambda. And yeah, this is about computational complexity. Here I say, yeah, if you just implement it, it's like, why not just use, why do we need a better version of TD Lambda? Why not use the online Lambda return algorithm by itself? And this is due to the computational cost of it. As I explained, it increases with the horizon. And so you want an efficient algorithm that directly jumps between these final values. And this is what True Online TD Lambda does. And yeah, so the derivation, you can sort of derive the True Online TD Lambda update equation. You can derive them directly from the online Lambda return algorithm. If you're interested in that, you have to look up the related paper to this, and you have the full derivation. But in practice, it means that you get these additional terms. So the black equation here is the regular TD Lambda algorithm, and True Online TD Lambda algorithm. You get these two additional terms, and these are computationally, they are not expensive. So computationally, the difference between regular TD lambda and true online TD lambda is, it's pretty much identical. It's just that you, with true online TD lambda, you get this exact equivalence with the online lambda return algorithm, which means you can set your step size much higher. So if you tune your step size, you can now use much higher values, which gives you in general much faster convergence. So it's overall, it's just a better method. Like there's no reason why you want to use TD lambda anymore, like the old TD lambda, like with accumulating traces. So this is called an accumulating trace. This is called, with the red part in there as well, it's called a Dutch trace. And so it's always better, basically. And we performed a whole bunch of experiments on all kinds of tasks. And true online TD lambda was always, at least when you optimize the step size, it's always at least as good or better than regular TD lambda. Yeah, so this is called a Dutch trace. And yeah, so here I showed, this is basically the empirical experiment that highlights what I just already said. So I show 3 versions of TD lambda. So the standard one is accumulate TD lambda. Like this one, things can sometimes diverge very quickly. So they made already a fix for that, which is replace TD lambda, but it has different disadvantages again. And so these two were the existing ones. Then you have true online TD lambda. And what I plot here is the normalized error. And you can show here that, well, you can see here that true online TD lambda in terms of error, it's always either smaller. So on some tasks, it's much, much smaller, or it's sort of equal to the error of the best of replace and accumulate TD lambda, but it's never worse. So, the long story short, if you're doing eligibility traces, always use this one, true online TD lambda. It's just simply better. Like I was making a case with Rich Sutton when he was writing the new version of his book to only show true online TD lambda and simply not talk about accumulating traces anymore, but he didn't want to go that far. But I'm still happy it made it into the book. Okay, so this is the first part. Let's check on time. I think I have till about, I have maybe 5-10 more minutes.
Yeah, sure.
So are there any questions about this part, this first part? I don't see the chat, but I'm assuming there are no questions. Okay, so let me just move on to for the last 10 minutes, I'm going to move on to nonlinear function approximation. So you might wonder, so true online temporal difference learning. So I showed this algorithm. This one over here, but I only showed it for the linear case. So you might wonder, is there a true online TD lambda for the nonlinear case? And actually there is not. So because while you can build the online lambda return algorithm for the nonlinear case, that's no problem. However, like the derivation behind it, deriving true online TD lambda, it uses that the gradient of like that the gradient doesn't depend on your weight factor, which is the case for linear function approximation. However, it's not the case for nonlinear function approximation. So it's impossible to get sort of an exact equivalence with the online lambda return algorithm when you're doing nonlinear function approximation. So exact equivalence is not possible, but you can do something something else which is very close to it. Yeah, so implementing the online forward view is computationally expensive, so that's not what we want to do. In the case of linear FA, yeah, there is this efficient backward view through online TD lambda. In the case of nonlinear function approximation, this does not exist. So we have this new research question now: is it possible to construct a different online forward view with a performance close to that of online lambda return algorithm that can be implemented efficiently? And the answer is yes. And basically, it uses an online lambda return with a fixed horizon that is k time steps ahead. So as a consequence, updates occur with a delay of k time steps. But now, you know, it's computationally efficient. So, and like this, this online lambda return, it's a very close approximation of the regular lambda return as soon as k becomes sort of larger than 10. So, you know, it's a very good approximation. So here again, I show the online lambda return algorithm, and over here, which is the red line, the offline lambda return algorithm, which is over here. And I have now this new method, forward TD lambda, that uses an online lambda return with a fixed horizon, and I use k is 15 here, and that you can see over here. So it's not as good as the online lambda return algorithm, but it's still a very decent performance. Well, then some notes on how to set k. Well, there is some trade-off here. You wanna, if you set k very large, then the delay in updates become very large. If you set it very small, it doesn't really approximate the lambda return anymore. So, you know, you want to set it something in between. And I provide an sort of a formula over here as a good rule of thumb, how to set your k value. And this is shows results on a mountain car task with nonlinear function approximation. So you have first TD lambda. So that's the standard TD lambda algorithm, where again, you see for high step sizes, things diverge. You have here the offline lambda return algorithm and the online lambda return algorithm. And the online lambda return algorithm ultimately it performs better for higher step size. It just performs better. And you see the forward TD lambda algorithm, it's actually even a little bit better than the online lambda return algorithm in this case. But overall, it performs very stable. So it doesn't diverge such as TD lambda, and it gets a very good performance, even better than the online lambda return algorithm. So that's, you know, if you want to do something like multi-step with nonlinear functional approximation, then the forward TD lambda is a very good method to use. So this was a prediction task. Here I show two control tasks where I built a forward version of chandar-lab, and you can see, so now what's plotted here is the return, and you can see that it compared to regular chandar-lab, it performs much better. Let's see. Okay. So the summary of this is that the online lambda return algorithm, you know, it outperforms TD lambda, but it is computationally very expensive. For linear function approximation, an efficient backward view exists with exact equivalence, which is true online TD lambda. For nonlinear function approximation, so efficient backward view does not exist. However, with forward TD Lambda, it approximates this online Lambda return algorithm and can be implemented efficiently for nonlinear function approximation. The price is that forward TD Lambda, there is a delay in the updates, but empirically, that doesn't really seem to hurt performance very much, because what we actually what we see is that forward TD Lambda it outperforms TD Lambda. Now, the one thing I should mention here is that the task that is showed here is mountain car task, and I think it was the pendulum task. So those are very simple tasks. Like the one reason why you don't see elicibility traces a lot with DeepRL is that DeepRL typically requires experience replay for stability. So you don't really use it for simple tasks, but as soon as you move to Atari problems, you need experience replay, and experience replay just doesn't combine well with multi-step update targets, because the multi-step update targets, they have sort of an because experience replay is an an off-policy technique, whereas a multi-step update target, it requires an online sequence of samples, and so combining experience replay with multi-step update target, that's just it's very hard to do in general. And so that's why you see some methods that use multi-step update targets, some DeepRL methods, but they all use a very short experience replay buffer. For example, if you have ABC with multiple.
Hello. Okay. But Ham, I have a question. So, like when you say it is hard to do eligibility traces with experience replay, is it an engineering issue, or even if you manage to do it, it doesn't work?
So you could make exactly the latter one. You can do it. You can make some implementation, but it just doesn't work well. The one-step method is going to outperform.
Sorry, can you please repeat it? Like the audio was not clear.
So you can implement it, but it's not going to work well.
Okay. So, but why doesn't work well? Like, is it because these transitions are from like off policy?
Yeah. So because if you have a very long experience replay buffer, so the experience collected early on in your buffer is from a very old policy. And so if you're taking a multi-step update target, you're using sort of a sequence of old samples to construct a multi-step update target. Now, this is not an issue if you're doing a one-step update target, because it's a fully off-policy update. But so even samples from an old policy, it doesn't affect how it doesn't affect the update target of a one-step update target. But this is when you're doing a multi-step update target, you're really, because you're using a sequence of samples which is generated by an old policy, there are sort of that old policy still has an effect of how that multi-step update target looks like. And so you're basically sort of introducing update targets coming from a very old policy. And so if you have either you use a very short update target, that can cause instability unless you sort of take different measures. You can't just use it with DQN for it.
Okay, thank you.
So this concludes my talk. So here are two papers to cover. Yeah.
Okay, thank you. Any questions from the class or in the Zoom? Any questions? Okay, well, if there are no questions, probably I have one last question. So does it make sense to think about off-policy version of eligibility traces?
So you could do that, but also like you need to do something like so you need to account for you need to use different weighting, and so you're gonna introduce variance again, which is gonna create a negative effect. You like it's not gonna work well if you do like offline, like off-policy multi-step updates. You need to do something like important sampling, which which increases the variance. And so, well, this is again one of the things you can do it. You can build a tool that does it. It's not gonna create huge benefits.
Okay.
I might have a question. So can you go back to the slides where you showed the offline method and the online one compared to the TD with the error between them?
Yeah. One moment. So, I mean this one?
Yes. So as we see in the graph, like the RMS error is like between the TD lambda and the online lambda, it's like quite the same, but until like at step 37, yeah,
Right,
we see like it falls apart, it diverge from each other. Is there like a specific reason why they can go both part ways?
I mean,
because
sort of it's the longer because it bootstraps from previous values, so things are slowly going to increase. So like the longer you run this, the more it's going to deviate, because at each update TD Lambda makes, there is a small difference with the update of the online Lambda return algorithm, and this just accumulates because you do these updates at every time steps. So the longer you go, the bigger the difference is gonna get.
Okay, thank you.
Okay, so, well, if there are no more questions, we can stop here. So thank you once again, Ham, for the great presentation. So since we ran a little bit late, we will stop here and continue at 11:45. So now we will get back to model-based reinforcement learning, and we will finish our discussion on model-based RL, and we will talk about how to do model-based planning with continuous action space. So thank you.